This podcast is supported by Siemens, your partner for industrial-grade AI.
Hello, everybody, and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber, and it's a pleasure to talk to
Peter Seeberg. Good morning, Robert. Good morning, afternoon, evening, wherever you are, dear listener. It's nice to have you with us.
Good morning, Peter. We were both on the road. You were in Munich at the machine learning conference. What did you bring back?
Yeah, that was a small road. It's I just gone on the fast train, the S-Bahn, as we call it here.
Yeah.
Which is, I actually live very close to the track. I mentioned that, I believe, in the
last episode with the drones. Yeah.
Oh, that's a test if you actually listen to it.
Absolutely.
Very good.
I do.
Oh, very good. Yeah, because I joined Machine Learning Week, was it 4 or 5 years ago? And at that time, it was in Munich. I recall very well. This time, I could not join the Sunday evening before, but then the 4 years ago, I could, and that's why I know it's so specific. And then it was in Berlin for 2 years, I believe. So we came back, they came back, and I was there as well. The first day I was there. Very interesting, as always, a very specific part that I moderated the industry track. But before then, we had Maximilian back. He did the keynote. Maximilian is a researcher, developer at NXAI, and he did the keynote presentation on XLSTM. He went into the details of what XLSTM is all about. It was sometimes rather detailed, but there were loads of questions, very well moderated by Martin, sitting very nicely together at the keynote at the end. Loads of questions which could not all be answered, not because Maximilian would not have been able to, but just because there wasn't enough time. So that was a great start. And then in the industry track, great presentations, great new stuff. Of course, loads of large language models, foundation models. One specifically that I recall done this time in a combination I had not seen, of course, knowing both Michael Haft and Eric Schwulera. And at this time, Eric Schwulera from Siemens, by using the causal AI approach from Michael, what he was really sharing is that he had even brought down his PPM, his parts per million defect, which is already very low in his PCB manufacturing line, but he was even able to bring it down a couple of points further. And I recall my specific question. I think my question was probably because Eric is in this area for 20 years, right? And are we now seeing actually algorithms moving kind of beyond the capability of humans? And I believe his answer was in the area of, yes, with a team of whatever number of people, many specialists in many different areas. So it's maybe still this little bit of a silo. A human can only know as much as they can know, with a manager sitting on top of it. And then if you give the algorithm in that combination with the causal approach, in this case by Michael, then the algorithm sees more than each of these highly specialized individuals and can help you even further.
Oh, wow. That's interesting, right?
Yeah, it was very good. Very interesting to see. The complete causal approach by Michael is very interesting. Not sure that I've completely understood it, I must say. Maybe we shall ask him again at some point in time. Of course, we know Michael.
We should ask both of them, yeah. Maybe Eric also.
Yeah, right. Because there's still all the time questions moving backwards and forwards, always on LinkedIn. How does predictive maintenance work? Does it work at all? And I do recall as well that I was asking for the specific algorithmic approach, which I believe, to be honest, the answer by Michael was more like it's more like organizing your data in a structurally new way. And I can't say more about it now. So yes, maybe at some point in time we should ask him about that.
Great. I was a guest at the Fraunhofer IPA to record a live podcast with Professor Dr. Frank Hutter and Professor Dr. Marco Huber. And Frank, you know him from our event AI in the Forest and his topic TAP PFM and AutoML. And he is founding a startup these days. Whoa, that's interesting.
On exactly those two topics, or?
Yeah, on TAP PFN. Yeah. And he didn't want to reveal any more than that, but I immediately demanded a podcast episode with him. Yeah, they are now checking some venture capital topics, I think. But yeah, quite interesting. TAP PFN, startup on TAP PFN. I was surprised. But he mentioned something at our event that he is planning to do something like that, I think.
Okay. So, well, at the end, we're going to be talking about Johannes and XAI. So there's at least some kind of similarity in my brain where we recall Johannes showing his picture a couple of weeks ago back at Stanford.
Yeah.
I think he's got a relationship there in that direction. And also the same looking back, having spent time at Google, right? So.
Yeah, Frank was, I think, at Google, right?
Frank was at Google, yeah, exactly.
Yeah, Frank was at Google. In keeping with our main section, as you mentioned with Johannes Brandstetter, Nvidia announces Omniverse real-time physics digital twins with industry software leaders. So all the buzzwords are there. So
Amazing.
Omniverse real-time physics, digital twins, industry software. And I have a quote. Very interesting quote. Blueprint for interactive virtual wind tunnels enables computer-aided engineering exploration for Altair, Ansys, Cadence, Siemens, and more. You also recognize the news, right?
Yeah, I did. Yeah, I mean, actually, the theme is very, very similar. You know, not sure that this is a correct way of comparing both, but one goes with, let's say, with a combination of CPU plus, of course, Nvidia. You know, their model software model standard. In this case, Omniverse, right? And the other one, which if you want, I can just give a quick introduction to what we're going to be listening to.
Yep.
So I did talk to Johannes. When was that? But I think I looked back 15 weeks ago. That was at the Siemens AI for Purpose Summit.
Exactly, yeah.
And at that time, we talked about the relationship between weather and simulation. We talked about, I mean, Johannes told us how, because he came from Microsoft, Amsterdam, Aurora, I think it's called, and how the weather forecast is changing structurally. And he was hinting at, you know, something similar may be happening in the world of simulation. So Johannes, being the chief researcher at NXAI, is also an assistant professor at where he's based in Linz, University of Linz. And so in the podcast you're going to be listening to, if that's what is your main interest while you're here today, you're going to be hearing nothing less but a revolution announced by Johannes happening in simulation by means of deep learning. Now, the way he puts it is that he sees it as an add-on to numerics, and maybe that's where the comparison between what you just announced, Nvidia, as I say, hardware, software, and he says, you know, the deep learning approach is going to allow for real-time digital twin simulation. He starts with this very specific world. The solution he has is called Neural DEM, DEM, but he is hinting that there's going to be similar other solutions in this space as well. So the direction is clear. It's going to be very interesting to see. Maybe that's another thing we should do, where we're kind of comparing to. Maybe at some point in time we should look at, you know, what does the one solution bring over the other.
Yeah, I think there's so much going on in this area right now. Every day, something new comes out from the big companies like Nvidia, from many smaller ones. From my point of view, the topic physics and AI, or the topics physics and AI, is the next big thing, I think. I'm not sure, but I think so. It's really, really, really big, I think, because everybody's now focused on that. Yeah. What is your opinion?
Yeah, well, it's all about the way Johannes puts it. And I think Action Jensen did something the same. I mean, they use the words of digital twin simulation, which is the same. And I think I talked about it before, having studied computer-aided design at that time in an architectural environment. this looking into the future has probably been as old as as humans exist, I guess. The weather is probably the most typical thing. We don't have to look back a couple of 1,000 years, but we have these farmer rules, right? Farmer rules which exist. They say, farmers say, and I'm sure they're not only here in Europe, they're everywhere where farmers are, and they go from generation to generation. It's based on knowledge that we gain over time. And I was asking you this morning as a start, how is the weather where you are? And the farmers know exactly if this and that happens this week and then the other week and then the sun and the rain, then in the next couple of days or weeks, this is going to happen. Now, that's not a pure science kind of thing. But the point is trying to look into the future, which I believe is that's a big thing saying, but probably that's what our industrial AI podcast has been all about for the last 6 years. And probably what it's going to continue to be about. We humans want to know the future. It's very good. We always say that we do not, as humans, know what's going to happen to us, right? But we know the problems of the world, and we cannot all solve them, but some of them we can by means of looking into the future. And that's what we want to do with simulation, with digital twin. And if we can make them real time, that's what Johannes says. There's very specific ones, and maybe that is still the difference between the one that was announced in Omniverse and the one that Johannes is here talking about. Sometimes you need to wait for days and weeks, which is maybe partly at least solved by Nvidia. And he says with the deep learning approach, you can make it real time. You can look on your screen and see the world that you're simulating.
We have discussed it so much, Peter. Let's listen to Johannes and to your interview with Johannes in the main part. Thanks a lot, Peter.
Thank you, Robert. Have a nice day. Have a nice day, dear listener, as well. And have you as a listener again soon. Thank you. Bye-bye.
Bye-bye.
Today I'm going to be talking to, once more, Johannes Brandstetter. He is assistant professor at the Johannes Kepler University in Linz, and I believe that's what he's talking today, chief researcher at NXAI. And Johannes and I are going to be talking about a Neural DEM, which is all about real-time simulation of industrial particulate flows. Hi, Johannes.
Hi, Peter. Pleasure to be here again.
For those that did not hear our first talk a couple of months back, please introduce yourself to our listeners, Johannes.
Yeah, hello, everyone. My name is Johannes. I'm here in Linz. I have a history starting in physics, did my PhD at high energy physics, like so many other people, switched to machine learning then, spent a couple of years in the Netherlands, worked at Microsoft Research, and approximately a year ago moved back to Austria, back to academia, also highly involved in NXAI, have the strong belief that AI is going to revolutionize the way we do engineering, the way we do manufacturing. And my take on this revolution happens deeply inside the simulation area. And this is where we are now, I guess.
That sounds great. We're going to be talking about revolution today. Yes, I do recall it's about 15 weeks later, I believe, episode 255. For those of you listeners who after this episode say, oh, that's interesting, I want to hear what Johannes had to say at that time as well. You and I were at the Siemens AI for Purpose Summit. We talked about weather forecasting. You say Netherlands, Microsoft. So for those of you, maybe we talk about it later. You can make the link if you want to. But I do recall you suggesting the same like you already used the word revolution would apply to industrial simulation. 15 weeks later, here we are. You and your team just published a paper in which you claim to have come to replace discrete element method, DEM, DEM routines and coupled multi-physics simulations with deep learning surrogates. That's a big claim. So just we all understand how big it is, let's start from the beginning. For those listeners not dealing with it on a daily basis, what is the discrete element method?
Yeah, maybe let's start from the very beginning. Thanks, Peter, for this introduction. So the problems we are looking at, I started to look at those problems approximately 1.5 years ago. And weather modeling at that point in time was pretty hyped already in the AI community. They were the first neural network driven weather forecasts, and those were like really large scale simulations running on the cloud and basically starting to replace or augment numerics. And for me, the first point was I was trying to figure out what is like a really tough problem to tackle, because neural networks work nicely on like image data, on regular data. But we all know from engineering that the data we have there, or the problems we have there, are not so nice. They are on meshes, they are non-regular, they are manifolds. Then we have all these different interactions of multiphysics and so on. So I put together my head with some of the smartest people I know from numerics, which actually happen to be here in Linz, which do this coupled DEM CFD simulations. I will say a bit more about that later. And we looked at some problems, and I like those problems a lot because they are high dimensional. So they have many particles. They have interactions of a fluid with particles. They are, of course, three-dimensional, so the spatial dimension is 3. They have a time dimension, and they are chaotic in a way. And I basically fall in love with these kind of systems because they are a challenge. And those systems we can now tackle, those systems we can formulate. We found a way how to deal with that. And for me, I think most importantly, a way how to scale this system. So the largest systems we were simulating have 500,000 particles and about 200,000 CFD cells. But if we go 10 times bigger, it wouldn't be a problem. We would just need more compute. We would just need more data. But just fundamentally, there is no barrier which we're hitting now. And that is important for me. I wouldn't say that what we build now can be already used in production and can be already used in engineering, because for that, you actually need to have a concrete problem to tackle, and we used rather famous and important settings from this community, but not specifically tailored to a problem from an industrial partner. But I would say that figuring out how to scale these networks at those problems is a very important step for us, and for me, it's personally a big breakthrough.
Now, today, engineers in simulations in exactly the area you talk about are using the discrete element method, DEM, integrated with, I understand, a grid-based computational fluid dynamics, CFD. Just 2-3 lines maybe on how that works today, and maybe also what are the advantages or maybe also potentially disadvantages of the way we do things today.
So that's the $1 million question. So DEM is really works on a particle level. So you model particle interactions, and you can think, for example, you can model sand, you can model grain, you can model food in a silo, you can model any type of material and any type of particulate flows. That's why it's called particulate flows. And these methods do not only have the power to really model such systems very accurately, then can also be relatively easily coupled to fluid dynamics. And often when you have systems like in fluidized bed reactors, which we're modeling, when air is blown in from below and is basically messing around with the particles, which you use for coating, for example, then you have to couple these two types of simulations. And this can be relatively easily done by DEM. And therefore, for this multiphysics, there is this specific DEM CFD coupling with which you can describe a lot of multiphysics phenomena. And yes, this is where we started. And also this coupling of CFD and DEM is where the Institute of Stefan Pirker and my collaborators Tobias Kronlacher and Thomas Lichtenegger are really experts.
You already mentioned 2-3 words. So we all, also those people not being themselves the simulation engineers, but maybe their colleagues are. You already mentioned a silo, you mentioned grain, sand, so I can get a little bit of a feeling. Nevertheless, it would be great if you could give us 1 or 2 typical use cases where finally this approach is being undertaken.
Yes, I didn't believe how important is silos for food industry, for example. But think of fluidized beds, where particles are in, and then the air is blown from below, as I said before. And this is extremely important in coating particles. So all big chemistry companies, they are really interested in this coating and basically in mixing of particles and so on and so forth.
Okay. Now, what is the disadvantage or moving into the new way of doing things with Neural DEM? What would you say is the typical DEM disadvantage?
Yeah, that's of course the next very tough question. So when I talk about numerics, I don't like the term disadvantage, because numerics has brought us very, very, very far. I mean, it started with Gauss, and there is so much going on, and we can model so many things. But I would rather say, what might deep learning add to this portfolio? And there is a few things which are not possible with numerics right now. And one of those things is definitely in the area of digital twins or real-time simulation. So think of, you have something like a furnace or any other system which you need to control in real time. And that is very hard, because you just cannot simulate that quickly. It takes you hours, days to simulate. And even with the best GPU-based accelerations, at some point you hit the wall in simulation time. And the more complex these processes are, the farther you get away from doing real-time simulations. And that is where deep learning has really the potential to shine. It allows you to interact with these systems in real time, to observe when systems get critical, but also to figure in how you as a human can interact with these systems and factor that into the simulations. And that is a huge potential towards real-time engineering.
Okay, thank you for kind of correcting me there. So I'm not going to be asking you to share with us how a neural DEM tackles DEM disadvantages, but rather, as I've learned, how provides neural DEM the add-ons, the way forward on top of the numerics as we have it today.
I liked it, yes. I liked it. Similarly, like the LLMs, right? They're not basically replacing our way we write, but they give us a new tool how to get more creative, or to come up with first drafts or whatnot, right? And similarly, it is going to happen in engineering. And the better you use those tools, the faster you can integrate them, the more advantage you have in the end.
So you want to share, not too detailed, because I have seen all kind of terms that at least the simulation engineers can, of course, should go to the paper. We'll make the link available, but just maybe a couple of lines on how your solution works.
Yeah, so I think there's basically two fundamental ideas which we needed to make that work. And the first is the representation. So think of these particle systems, and we were really always, I mean, the largest system we were simulating was 500,000 particles. But we always had to, in our minds, what is happening if we go to 10 millions, to 100 millions? How can we make sure that our method somehow still works? And it's just the scale, meaning that we just need more compute and bigger networks. Similar to what is going on in language and in other domains. And therefore, we kind of were blocked by this particle representation, because more particles means just more for the network to digest, and that is not scaling very well. So we came to the conclusion that we have to get rid of this particle point of view. And so we represent to our network everything as an underlying field. You can think of, as people did in the beginning of the 20th century, to think of the ether, so some field which perpetuates space and time. And we were using this field-based approach, which we cannot really formalize, but which we can use the network to represent the data and to get a loss function on to model our problem. And this approach is much more scalable, and it turns out much more stable to train. So really making a fundamental switch from the representation of particles to a representation of an underlying field, which might not even exist, but it's for the network, it's fine to learn this underlying field, and it can do it extremely well, as we've seen and has been surprised actually. And the second one is using the power and might of deep learning by projecting the problem to a lower dimensional space and using different interaction mechanism of this space. So which type of physics or which type of modalities interact with each other, we can model very nicely in this down projected space. And both of these approaches are really tailored towards scaling.
Okay, and the second one, I understand, is that related to or even based on the paper you did before on the universal physics transformer? Or?
Exactly. It's basically the same idea extended to multiphysics. Some very smart people, Benedict, Samuele, Tobias, working on that, and they really brought it to the next phase. And actually what is very exciting with this approach, we were now able, I'm not spoilering, but to really go to other domains away from discrete element methods, other simulation domains. And it seems that we kind of starting to converge towards a recipe which works for many different types of problems. And that's actually what excites me the most.
Okay, so is it correct to say that Neural DEM is based on the universal physics transformer and that we may expect in the future maybe other solutions like Neural DEM in other simulation areas?
That is very likely to happen, yes.
Okay, I'm not going to ask you further, but it's great to hear. Okay, let me see. You keep it at the correct level. I'm certain that you could bring it to a lot more detailed level. But as I said, that's for the specialists, for the simulation engineers. I would like to understand from you then, we talked a little bit about the use cases. What are the market settings in which Neural DEM will find usage? Or to put it differently, for what type of companies, I think, do the simulation engineers that will be using Neural DEM, what do they work for?
So most interest is coming from chemistry companies, using for coating, using for mixing. There is a lot of interest from metal industries. And yeah, maybe what I should say is this is really at the early stages, because there is to do DM with deep learning is what a few people tried, but most approaches, like, they got stuck at 5,000 particles. So it's a bit surprising for people that 1 million, 2 million is actually not a limit anymore. So I think it needs a bit of understanding. We have a lot of conversations and everyone is like surprised that we can model this. I would say I've never been in a spot where we show something and people are actually asking questions like, you can model that, really? So I think it needs some time to sink in and to develop the momentum for that. But as I said, that's why we chose these really hard problems to have a good starting point when we finally are able to do them.
Okay, so I understand this is kind of, this is your initial announcement, as you say. The market, the potential users need to get used to the idea that this is now possible. So maybe we're going to find and see further announcements in the near future. So maybe you do not yet know in detail, but I'm going to ask you what your thoughts are around, because I know from related solutions, algorithmic solutions in your company. So how about NeuralDEM? Is it going to be open source? Is there a patent? Are you thinking of eventually selling it as a product? Maybe all kind of questions you haven't decided, but nevertheless, I would appreciate your current thoughts on them.
Yeah, so NeuralDEM, obviously we believe in open science. For NeuralDEM, obviously we've written a paper and we share that with the community. At some point, we will also share models and basically let people play around with them, because people need to see what they can do and what the potential in them. And this is how we will move forward. So there is no way in holding these things back. You have to share and you have to let people play with them, that they get as excited as we do.
Okay. When you say you're moving now beyond the 5,000, maybe to 1 million or to a couple of million, no limit maybe to the size, does that mean when you're training, when you're modeling, where is that happening? Is there a cloud partner that you're doing that? Are you doing that within the area of the university of NXNI or?
Yeah, this is over cloud computing via the company, exactly. And we are reaching the phase where we can tackle these problems, but now it's time to think about what is like a more generalist solution to these problems, that you, in the end, what you don't want to have is some specific sort of problem for a specific sort of customer, specific sort of company. You want to have something more general, which is like more a general recipe. That's my midterm goal, which can be applied to several processes, to several companies, to several problems, and really a recipe how to build that, how to fine-tune that, how to train that, and so on and so forth. So I would say along those lines, we are making progress now.
Okay, tell us a little bit about your environment, your team. You're based in Linz. You mentioned 2-3 names. Who are the people working in your team, and are you maybe looking for new colleagues? And if so, what should they bring?
Yeah, that's great. So I can give a shout out again to my colleagues. So one person who was really driving that was Benedict Alkin, the first author. He was also my first PhD student when I came back to Linz. So basically, he who wanted to work with me. He was very eager to work with me. Together with him, we did the universal physics transformer. He's a very smart person and extremely good at scaling deep learning. That's where we really hit it off very well. And then at this team, we added Tobias, Thomas, and Stefan from Stefan Birker's lab of particulate flow modeling. They've been extremely helpful. Tobias has basically led this project from the numerics perspective. It was very fun for me to work with so many experts, so that actually what we're doing was meticulously proofread or cross-checked by numerics people. I mean, this is super important because in the end, you want to know if you're impressing yourself or if you're impressing the community. So it took us some time to impress them, but it was extremely nice working environment. And then last but not least, we have Samuele from Amsterdam. So I basically asked him to join us for an internship, and he performed extremely well and was a very vital asset to the team. And I knew Samuel since some time, so I knew that this would work. But I'm extremely proud that now people from Amsterdam coming to Linz, that they participate in this project, and really their expertise is also shining.
Okay, so you're moving forward, I assume, looking for other people to join, and what should they bring, if so?
Yeah, so there is a few domains I'm interested in. I cannot share everything, but obviously computational fluid dynamics is of big interest for me. I basically, the game we play with element methods, where you want to go for millions of particles. In CFD, you want for millions, tens of millions of grid cells or mesh cells where you run your simulations on. Then this same game we play in these domains, and therefore experts are needed both in numerics but also in scaling these deep learning systems.
Okay. So, well then, coming to a close, how is Neural DEM by replacing, is it replacing, or maybe it's extending, I believe I've understood in the meantime, maybe extending, replacing discrete element method. How is it structurally going to change the world of simulation?
Yeah, there is basically two changes which will happen. The one time is real-time engineering, so you can interact with the real world. Digital twins are floating around since a couple of years, but especially for this more complex and large processes like fluidized beds and many more. This is basically the way I imagine myself that this is going to happen. And that gives you better control, better process cycles, and so on and so forth. The second change is in real-time optimization, because if you have a fast surrogate, your engineering progress is much faster. Think of, you want to design certain geometries or certain processes, and if the simulation is extremely fast, you can test a lot of different parameters, a lot of different materials, and then pick what material basically fulfills all the properties you want. And if so, you can run the final set with standard numerics to make sure. But these two things are a bit opposite. So real-time digital twins and optimized process engineering. And in both ways, approaches like Neural DEM will be the key to achieve that. And we've seen that in the paper, that we can seamlessly run the process for different angles. So for different geometries, in that case, for different interactions, which means different particles. And the model is very, very flexible in running those parameters and gives you the correct answer for a wide range of different parameter sets. So these are the two things. And at some point I was really amazed how well this deep learning model can actually capture this different physics, because in the end, it's really different physics which we're modeling without telling the model what type of physics it is. To close, I think we are pretty far in this process, and lots more exciting stuff is going to come.
We can sense your excitement, Johannes. It's great to have you with us here. You promised at the beginning a revolution. You talked about it, and we're really looking forward to see simulation become real time. That's what I take away here. I hope you agree with that one.
Yes.
Thank you very much. Listeners that want to get in touch with you can best do so through LinkedIn. Otherwise, if you, the listener, have any question, comment, as always, please send a short email to peter@aipod.de. Happy you've stayed with us so far. Looking forward to have you with us again. And Johannes, thank you very much. And please keep us updated on the revolution you started in simulation.
Thank you very much, Peter. It was a pleasure.
Bye-bye.